Okay, so before I even start explaining anything, check out the first link in the description. There, you can try out this demo for yourself, right there in the browser, works on keyboard and controller, so you can decide if the rest of this talk is worth listening to. So you might have already noticed that the game is basically a heavily simplified version of Trackmania, and you may be wondering what the purpose behind just making a cheap clone is. So for a bit of background, I want to talk about the loaded arcade versus simulator debate. Simulators, of course, try to replicate reality, which gives you some amount of real-world data to compare against. Arcade games, however, try to replicate fun, which is subjective and hard to quantify. But what if we treat a game, like Trackmania, as our reality to replicate? My goal for this project was to basically reverse engineer Trackmania, but with respect to simplicity rather than accuracy, to create the minimum viable racing game with as little complexity as possible that's still engaging to drive. So, how does it actually work? First unusual fact, there are no raycasts and there is no suspension. The car is basically just a zero friction slab dragged across the floor. And yes, as you can see, vehicle physics can't function without suspension if the driving surface is flat, which is actually not an unreasonable assumption to make. So to give an overview, all we have to figure out is, for starters, what I consider to be the three fundamental forces of vehicle physics, which are engine force, deceleration force, and cornering force. And on top of that, we also have a few Trackmania-inspired support forces. We also need to figure out the engine sound and the camera. We have to decide on the exact parameters or magic values for all of the above. We need to pinpoint exactly where on the car to apply all these forces. We have to build a track to properly test the handling. And lastly, there is the standard stuff like graphics, UI, and timekeeping. So let's just get started. How does the engine work? Literally just constant force application at the forward direction of the rear tires. So no torque curves, no gear ratios, no differentials, we don't need any of that. And countering that, we have deceleration forces, which is just the sum of braking and drag. And drag essentially just resists the acceleration and makes us lose speed if we go off the gas. But applying constant acceleration as we do now is very counterproductive for immersion, because real cars noticeably lose torque as they speed up. To fix this, I simply created a lookup curve that takes the current speed as input and returns a drag force multiplier as output. And I found that keeping this curve linear was perfectly fine to maintain immersion. And finally, braking acts as an additional constant force in that exact same backward direction. Next up are cornering forces. But before we talk about actual forces, we need to talk about steering, because the fundamental problem of mapping a steering wheel input onto a controller or even a fully digital keyboard is non-trivial. You have to strike a balance between car stability, so it should not be too twitchy, like we saw here, and responsiveness, so it should also not be too sluggish, like we saw here. And this turned out to be one of the more challenging aspects. In principle, you just have to decide how far you should be allowed to turn the wheel and how quickly you're allowed to turn the wheel to balance these aspects. But as it turns out, at low speed, response is the most important, since low speeds are already inherently stable, but at high speed, the opposite is true, and stability becomes more important. So what I and many other racing games do is that the maximum steering angle gets lowered as the speed increases. So we need another lookup curve with speed as input, but this time with the maximum steering angle as the output. I also started with a linear curve here, but quickly realized that it was still a little bit too twitchy at higher speeds. So I went one step further towards something resembling an exponential drop-off instead of a linear drop-off, and that worked much better. Okay, so now that we can precisely point the tires in the right direction, we can start applying cornering forces in the sideways direction of the tire. But how much force do we actually apply? That is pretty much the million-dollar question, and there are many different answers to it, in the form of tire models. Two of the most famous tire models are the Passeca model and the brush model. Oh, and by the way, I know this slide looks like a meme, but simulating a tire as a paintbrush with lots of small bristles deforming is literally what happens in that model. But anyways, both of these models are more advanced than what we actually need. The simplest solution would give us just a single variable to define how much grip we want. And we can accomplish this with what I refer to as the damper tire model. Real cars have dampers to prevent the springs in the suspension from bouncing when going over bumps, so they basically counteract the movement of the spring, and that's exactly what we want to do with the tire as well. Imagine that we are going straight, we turn the wheel, but we're driving on ice with literally zero grip. What happens? Nothing, of course. We keep going straight on and the tire is slipping, which means the tire doesn't go the way it's pointing. And this slipping is exactly the thing we want to dampen, because we don't want to slip excessively. But what is slipping? I will go more into slip angles later, but for now I'm defining it as the tire's velocity in its sideways direction. So with that definition, we can measure which way and how much we're slipping, reverse the direction to create a damper, and then multiply that damping force by the amount of grip that we want. And this damping effect will prevent the car from feeling like it's just driving on rails and there is no challenge, because cars are enormous heaps of metal that can't just change direction instantaneously. So allowing that in even the most simple driving model would destroy any sort of immersion. In more complex simulations, you have topics like weight transfer and tire deformation preventing the on-rails feeling, and the tire damper is basically an approximation or a simplification for all of that. And that is literally the entire tire model. If you played my demo from the beginning and thought it was good, then congratulations, this is all you need to make a viable racing game. It's easy to understand intuitively, it's super fast to compute, it's trivial to adjust the amount of grip, and it doesn't break down at low speeds like many other models. The downside, of course, is that it's very static, so it's not going to do any crazy tire lockups or mid-corner snap oversteer, but on the other hand, you probably wouldn't be able to control that on a keyboard with digital inputs anyway. Many racing games try to make it more drivable through assists and things like that, but then you also have to ask yourself, what is the point of a super advanced tire model if you're just gonna smooth over all the intricacies of it anyway, to make it work on something that's not a wheel? There are games who manage this balance well, of course, so it's not like advanced tire models are completely useless, but they really are exactly that, advanced. And they should therefore not be the only thing that gets discussed with regard to designing vehicle physics, which is what I'm hopefully able to demonstrate here. But also, feel free to disagree with me on this point, because I would actually love to see more discussion around this. But even we are not quite done with the tire model yet, because keeping it entirely static would also be a wasted opportunity, and that's not what Trackmania does either. Because as you will know, if you've played it, it does feature a subtle brake-to-drift mechanic. You're rarely going full-on sideways, but you often just tap the brakes to get that last bit of extra rotation. And how do we get more rotation? If you're familiar with building setups in racing sims, you probably know the answer. By lowering grip on the rear, of course, which you can now do trivially. So we simply write some code to lower rear grip by a few % when we tap the brake to enter an alternative drift mode. However, we also have to get out of the drift again. So we basically have to detect when a drift is supposed to end so that we can restore grip back to normal values. For this, we can use the so-called slip angle that I already hinted at, which is the difference between the direction the tire is pointing and the way it is actually traveling. The higher the slip angle, the more we're drifting, and we get a concrete numerical measurement for that. So we can just decide that if we're less than 5% of the way towards fully sideways, we want to exit the drift state again and the car should grip back up. And that concludes my explanation of the tire model and what I consider to be the 3 fundamental vehicle forces. So now we have the final force values that we can apply to the car's rigid body. But where exactly do we actually apply them? Well, normally you might think they should be applied at the wheels, but recall that there actually are no wheels, no physical wheels and not even raycast wheels. We could just position them exactly where the visual wheels are, but we don't have to for the physics to work, and that gives us a lot of flexibility. So our wheels are really just more or less arbitrary points in 3D space relative to the car, which has its own dimensions we have to decide. And the wheel axle width, as well as the wheelbase length, of course also influence the handling. Although I'll admit that I really just picked values that seemed plausible enough and didn't really think about it beyond that. Much more important though is the height that the wheel sits at, and because luckily everything is just virtual, the wheel can literally sit inside the body of the car with no issue. This is convenient because if we position them at the middle of the car by height, we completely prevent the phenomenon of body roll, which can actually cause unintended rollovers if you don't also code separate anti-roll bars. Oh, and speaking of car dimensions, I also had to make sure that the dimensions of the physics engine hitbox roughly matches that of the car's 3D model. So this is the point where most other vehicle physics tutorials or talks would just end with a car you can drive on flat ground and let you figure out the rest, which always annoyed me, so of course we keep going. And we keep going with what I call support forces, because there are still a few things missing to get closer to Trackmania. The most complicated of these forces is wall collisions, because while game engines already have rigid body collisions built in, it doesn't mean they're necessarily suited to driving games. Out-of-the-box physics kind of just throws the car around and also rewards wall riding, which Trackmania definitely doesn't do. Instead, hitting a wall just takes away a chunk of your speed, basically just another damper. So to replicate this effect, we measure wall impact velocity, scale it down to a percentage, and then subtract that from the car's velocity. And we do the same for angular velocity to prevent the car from spinning erratically, to also make it more consistent and predictable. And beyond that, we have 3 more extra forces, but luckily they are incredibly simple. And the first 2 are about in-air stability. If the car is in the air, we firstly apply a slight forward torque, which pitches the nose down to land more steadily. And secondly, we also add extra gravity to the car, so it doesn't jump unreasonably far, like it does on the left here. And the final extra force is simply a small multiplier to the engine force if the car is driving downhill, which is also present in Trackmania and just adds a bit more excitement to those sections. And downhill is a good segue to a challenge I encountered when programming the camera. The camera is probably one of the more underappreciated aspects of racing games, and games in general, because you only really think about it if there's some obvious problem with it. The algorithm for my implementation, which I'm calling the trailer camera method, basically maintains a consistent distance by pulling the camera toward the car along the line between the two, creating this pulling a trailer effect. But you have to disable this pulling effect on the vertical or y-axis, because otherwise the camera would just get dragged along the floor. Instead, we lock in a fixed target height, but add a little bit of lerp smoothing to the camera so it can dip slightly on slopes before smoothly gliding back up into place. And I found that this is very effective. So now we have the physics and the camera, but the final piece of the car puzzle is engine noise. So what's the simplest way to get passable engine sound? Using existing recorded samples from real engines could work, but comes with licensing headaches, and from scratch audio synthesis is complex. But despite knowing next to nothing about synthesis, with some AI help I discovered that if you set a bass frequency, lay a few multiples of that frequency, known as harmonics on top, modulate them a bit, and optionally add an effect known as soft clipping, you actually end up with something that's a reasonable approximation of an idling engine. And what you can do then is just increase the pitch as the car goes faster. Here, take a listen. You can also add fake gear shifts at different speed thresholds, with some lerps moving at those thresholds, and you end up with the final sound from the game. And that concludes the entirety of the algorithm that controls car behavior and everything related to it. However, the algorithm on its own is really only the first step towards good driving feel. And this is also something that's rarely talked about, I feel like. I've already touched upon the Passeca tire model, which we aren't using, but many other games are. And if you take a look at its most basic form, you'll find 4 different parameters that you have to set. So that begs the question, how do you figure out what those parameters should be? And the answer is, unless you happen to have secret industry insider knowledge, you just have to guess, see what feels right, and iterate. And this is what I refer to as the parameter soup problem of vehicle physics. And as you get into more advanced versions of the Passeca model, this gets much worse, because side note, the Passeca model has actually seen increasingly complex iterations over decades, instead of just being a single coherent thing. Even for Simple Race, which is literally designed to be the minimum viable racing game, I counted over 30 different parameters and 2 curves for which I had to make a decision on the final values. And if I were to give you this algorithm with all these values set to 0 and ask you to find good parameters, you would probably be completely overwhelmed and not even know where to get started, despite already having the correct algorithm. And this is exactly why it's so incredibly valuable to have a target you can aim towards, whether that is the real world or another game that already exists. Like during development, I would literally just sit there measuring acceleration times in Trackmania and try to replicate them by tweaking Simple Race parameters. And that can be quite tedious as well, because it really starts blurring the line between engineering and art. So that's why I want to encourage anyone else to try and mess around with these parameters. I think I found a good starting point, but still, experiment and see if there could be another set of parameters that makes the game even better without even tweaking the underlying algorithm at all. But how exactly do we make an informed decision about these parameters? Because if we just leave everything as is, driving a car on flat ground without any external frame of reference, how on earth are we actually supposed to fine-tune a steering angle curve? How do we get a feel for if the handling is too sluggish or too twitchy? And on flat ground, we don't, of course, so we have to add a testing track. And ideally, one that actually challenges us to push the car to the limit, because only if we have an objective we want to achieve can we actually make a judgment on whether a parameter change was good or not. And I also wanted to have different time trial medals in the game to establish a benchmark for players to chase after, because only such an objective can turn a going in circles simulator into an actual video game you want to play and get better at. So when making a track, being a Trackmania clone gives us another big advantage, because all of its tracks are famously constructed from predefined pieces that you simply stitch together into a track. That makes it easier to recreate any track with a 3D modeling program, and probably also avoids licensing headaches again. D14 Endurance is my personal favorite, so that's what I decided to go with. And what we know is that the base size of a Trackmania block is 32 by 32 by 8 meters. And I reasoned this has to mean that the track has to be 22 meters wide with 2 meters of padding on each side, 2 meters of barrier width and 1 meter of margin on the outside. And with this knowledge, it is simply a matter of 3D modeling the pieces and snapping them together, which I was luckily also able to do with an AI-generated Blender script. One where everything I just said is also parameterized. So in theory, as long as you use the same standard pieces, you should be able to make your own track 3D models just by assembling this admittedly impossible to visualize puzzle inside a Python list. And that is pretty much everything. I could also talk about 3D modeling the car, doing the UI, or writing the gameplay code to count the time and laps and so on, but I think that stuff is comparatively easy to figure out and not really worth talking about. But it is, of course, there in the linked GitHub repo if you want to take a look. The code is MIT licensed anyway, so you can do whatever you want with it. And the car and track 3D models are also under Creative Commons 0, so also no restrictions there if you want to use those. So now we're approaching the end of the presentation, and if you're now watching this and you're still sort of new to game development, you might, just like I used to when I started, be asking yourself, okay, so you explained all those forces and the concept sort of makes sense, but I still don't really know how to get started with actually implementing any of this. If this is you, then feel free to let me know, and I might make a full Godot tutorial if there's demand for it. But even without a tutorial, like I said, all of the code is open source and all of the vehicle physics are in a single file. So if you want, you can just paste that into any AI chat app and get explanations for anything you might be confused about. Especially because the vehicle script is literally only a little over 100 lines of code. And that's exactly how I like it. Just make sure you actually use one of the recent and powerful models, but I'll also put some links in the description as well. So I hope this presentation helped some of you, and if you want to know where those exact medal times come from, you can check out my last video about racing trials. And also make sure to like and subscribe if you want to keep following my journey to bring back awesome racing games.